Hi, and welcome back to my Physics Online video series. Today's lecture video is about sound intensity level, the decibel scale, and all that. This is an algebra-based physics lecture. So for what a lot of people would call college physics. And we're continuing with our discussion of sound and sound as a wave. So let's dig into that a little bit. Now, at this point in your physics course, in the semester, your physics career and so on, you've talked about energy, you've talked about power, and we've now talked about waves, and we've talked about also sound waves. And there's another term that we can now introduce for sound waves. And that other term, the basis for it is, if you consider a sound wave, you have a person, let's say, and so here they are, and they're saying something. Like so. And whatever it is that they're saying, the sound that they're making basically propagates outward from them in all directions. It actually also propagates behind them, but to a lesser extent than in front of them. So if you are standing, let's say, 3 feet in front of a person who's speaking, and you're standing 3 feet behind a person who's speaking, then you'll hear different loudness. You'll hear with different level of volume whatever it is that they're saying. In front of them you'll hear it louder than if you're behind them. But once you have that little caveat aside, the sound waves basically propagate more or less uniformly once you're out in front of the person. And if you were to make sound some other way, like take two things and bang them together like that to make sound, and this point of contact where the two bang into each other, that's sort of the source of the sound, is basically a point-like source. So over here, here's my source, and the sound waves basically propagate out away from that source in all directions. Okay? So there's a certain amount of energy that goes into making each of those sound waves, each of these, we could call them like a wavelet or a wavefront, maybe would be a good word, or single wave cycle, single cycle of the wave, whatever you want to call it. A certain amount of energy that's being carried by that wave. Okay? And that energy is more or less conserved. It may be absorbed by the air, it may be absorbed by collisions with the wall, or with, like, something like me, or my smooth shirt, something like that, my soft shirt, a carpet, all that. So it eventually does damp out. But by and large, the energy within this wave right here, the wave represented by this circle, and the energy in the wave represented by this circle are equal to each other. Okay? There's less than 1% difference after it's propagated a few meters like that, as long as there's no nothing to absorb, like a ground or something like that. Okay? The amount of power taken to generate each of these waves is equal to each other. But if you're standing over here and listening, and somebody else is standing right here and listening to the same source, the same sound, this person right here is going to hear it more loudly. So this is louder, this person is going to hear it more quietly. This right here being the source. Why is that? If they have the same amount of energy and the same amount of power, why do we have different volumes that we apparently hear the two waves at? To understand this, we have to introduce a new term. And by way of explanation, let's consider how it is that we interact with the two waves. If I'm standing out here, I have an ear, my ear has a certain size to it. I'm catching only a certain fraction of the wave on my ear. It's only a certain part of it is incident on my ear and therefore can interact with my eardrum. This part of the wave out here is pretty far away. It's not interacting with my eardrum. This part over here is not interacting with my eardrum. This part right over here is not interacting with my eardrum. Maybe only this section right here of the wave interacts with my eardrum. If I'm standing over here instead, though, that same eardrum, that same ear, same size, has a larger fraction of the total wave incident on it. So if I were going to compare how much energy actually goes into, or how much power actually goes into my ear from the wave, it should be evident that more of the power goes into my ear from this wave than from this wave. Okay? So basically, I'm taking up a larger and over here a smaller fraction of the total basically sphere. These rings represent spheres occupied by the wave. So what I've done here is I basically need a new quantity that, instead of just being energy or power, can represent how much energy or power per unit area. It turns out that we have both quantities. For energy per unit area, we have what's called fluence. And this is energy per unit area. For power, we have what's called intensity. So intensity is power per unit area. Now, of these two terms, the one that you're actually going to want is the second term right here. Fluence is sort of a special topic that, as far as I know, isn't really used much for most waves. Intensity is used for most waves, sound waves, but other types of waves also can be described with intensity. We just usually introduce it here with sound waves. Fluence, as far as I know, is mostly dealt with in the field of optics, especially ultrafast optics, because in ultrafast optics, high intensity optics, you can have a very intense amount of light incident at a certain point while having not much fluence present. And the reason being that power is energy per unit time, and therefore you could have a very small amount of energy, but also in a much, relatively speaking, shorter amount of time. If I have a millijoule of energy, that's not very much energy, but if I compress that millijoule to a femtosecond, then that's very high power, and consequently very high intensity if I focus my spot down. But it may or may not do much damage because there's not much total energy there. It can damage like a small part of something. But if the fluence is higher, then it's going to do a bit more damage as well. Okay, so with that little caveat aside, in equation terms, intensity is defined as power per unit area. I'm going to use an S for area just because a lot of people's books are using A for amplitude at this point. Ironically enough, when you get to later in the semester, you have S for the pointing vector, which is actually equal to the intensity of your electromagnetic radiation. But for right now, S is area. You could think of it as surface area. So S represents area. P represents power. Recall that power is defined as work per unit time. So delta W, how much work, over delta T. There's not really a delta with the P, but sometimes there's an average there. Okay, so this right here defines intensity for us. Now it turns out that the units, by the way, units are in joules per second per square meter, which is defined as watts per square meter. So we could say watts per square meter. Or we'd represent that by a W over an M squared. So for example, if I have a 3-watt source and I stand 3 meters away, then my area would be the area of a sphere of radius 3 meters, so 4 pi r squared, 4 pi times 3 meters squared. And the result is that my intensity would be 3 watts divided by 4 pi times 3 meters squared. If you throw all that into your calculator, you get approximately 0.02, let's say 65, so 0.027 watts per meter squared. Now with sound waves, as it turns out, and especially for our hearing, we have a pretty large range that we can hear. We can hear sounds that are as quiet or even sometimes quieter than 10 to the minus 12 watts per meter squared. So threshold of hearing at 1,000 hertz is about 1 times 10 to the minus 12 watts per meter squared. We actually define 1 exactly times 10 to the minus 12 watts per meter squared as the threshold of hearing, even though at certain frequencies we can actually hear quieter, like a lower intensity sound. A very loud rock concert might be 10 to the minus 3 watts per meter squared. A jet engine taking off from, several tens of meters away might be about 1 watt per meter squared, etc. So it's convenient to define all this in terms of what's called the decibel system. So beta is called intensity level, and it's defined as follows. Take 10 times the log base 10 of the actual intensity divided by the intensity threshold. That's your intensity level. That also means that the difference in intensity level is 10 times the log base 10 of one sound to another sound intensity level. Okay, so for every 10 decibels that you increase in intensity level, you're going up by a factor of 10 in intensity. For what it's worth, a delta beta of about 3 decibels is about factor of 2 increase. Similarly, if we want the intensity from the intensity level, then here's what we do. Since beta in decibels is 10 log 10 I over I naught, then I must be 10 to the power of beta over 10, and that covers it.